Hello, welcome to chapter 10. This is the last chapter that we're going to be working on this year, and we're probably not going to do everything, but we're going to start learning a little bit about sequences and series. And in this first topic of chapter 10, we're focusing on sequences and how they can really be thought of as representing a function. So in the past, we've talked about linear and exponential functions. Today we're going to talk about two kinds of sequences that relate to linear and exponential functions. Arithmetic sequences, which relate to linear functions, and geometric sequences that relate to exponential functions. We're going to talk about both of those. There's a lot of vocabulary in this section, so make sure that as we go through, at the end you know how to define each one of these things. All right, so in math, a sequence is just an ordered list of numbers. So it's just a list of numbers in a specific order. Each separate number in that list or in that sequence is called a term. And then we have finite sequences and infinite sequences. Really easy to tell the difference. A finite sequence has a finite number of terms, so it ends. An infinite sequence goes on forever. It has an infinite number of terms, right? Each term in a sequence we say is a function of its position. So in this sequence, the first term is 1, the second term is 3, the third term is 5, the fourth term is 7, and so on. So the domain is the set of natural numbers, 1, 2, 3, 4. So the domain is which term number it is. So like f of 1 equals a1. So in my sequence up here, f of 1, if I plug in 1, my first term is 1. F of 2 would be 3, and so on, meaning the second term is 3. The third term would be 5, and so on. So my x values are the term numbers, and my y values, or my range, are the actual values in my sequence. So a sequence is a function where the domain is natural numbers. Remember, natural numbers are 1, 2, 3, 4, and so on, not including 0. The range is all real numbers. It can be anything. So the domain we usually denote with n. N is which position is my term in. Is it the first term, the second term, the third term? And a sub n is what is the actual number in that position. So if we look at this sequence here, the domain is 1, 2, 3, 4, 5 because there are 5 terms. And the range is 3, 6, 9, 12, 15. Those are the actual numbers. Here, my domain is all natural numbers because it goes on forever, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on. And my range is all y values that are multiples of 3 because this sequence has a pattern, 3, 6, 9, 12, and so on. We're going to start by focusing on arithmetic sequences. An arithmetic sequence is a sequence where the difference between successive terms, that means terms right next to each other, is constant. That difference is called the common difference. Make sure you write down both of those definitions on your notes. To find the common difference, we subtract any term from the term that comes after it. And to find the next term, we add the common difference. So let's look at an example of what that would be like. We're going to figure out whether or not this sequence is arithmetic. So here, to get from -3 to -8, I subtract 5. To get from -8 to -13, I subtract 5. To get from -13 to -23, I have to subtract 10. Since that is not the same as both of these -5s, there's no common difference between my terms, and so I have to say that it is not arithmetic. Now if we look at this one, then we start to analyze it. Each of these has a common difference of 6. I add 6 to get to here. I add 6 to get from -2 to 4. I add 6 from 4 to 10. So this is an arithmetic sequence, and it has a common difference of 6. So an arithmetic sequence is really like a pattern that we're looking for. So you guys try this one. All right, you should have said that yes, it is arithmetic, and the common difference here is 11. And in this one, it is not arithmetic, because from 22 to 14, we are subtracting 8. From 14 to 6, we're subtracting 8. But then from 6 to 2, we're subtracting 4. All right, now we're going to look at what happens if I graph an arithmetic sequence. Here we have the arithmetic sequence. They're telling me it's arithmetic. -8, -6, -4, so the common difference here is +2. I'm adding 2 to get to the next term. They want us to find the next 4 terms. So to find my common difference, remember I can take any term, in this case -4, and I subtract the term before it. So here, it was pretty easy to tell without doing this, but -4 minus -6 gave me +2. That's my common difference. So I'm just going to keep adding 2 until I get the next terms. So here are my first 3, -8, -6, -4. I keep adding 2 to -2, 0, 2, and 4. So those are my next 4 terms. Now what we want to do is we're going to graph the first 7 terms. So remember, my domain is just the natural numbers. How many terms are there? 1, 2, 3, 4, 5, 6, 7. I'm going to graph the first 7 terms. My range are the actual values, -8, -6, -4, -2, 0, 2, and 4. So I have to graph my corresponding ordered pairs. My first term is -8, so that's the ordered pair 1, -8. My second term is -6, so that's the ordered pair 2, -6. My third term is -4, that's 3, -4, and so on. You'll notice that this makes a linear pattern, a straight line. That's because of the common difference. The common difference is my slope, right? This is a line with a slope of 2, just like my common difference. So the term number n is the independent variable. That's like my x. A sub n is y. The common difference is my slope. So an arithmetic sequence will always graph like a straight line. Okay, you guys try this next one. Okay, your next 4 terms should be 5, 14, 23, and 32. You get your common difference here by taking, let's say, -4, subtracting the previous term. -4 plus 13 is 9, so 9 is my common difference. So -4 plus 9 gets me to 5, plus 9 to 14, and so on. Now try graphing. Which graph matches that? Okay, you should have chosen B. Again, my x values will be 1, 2, 3, 4, 5, 6, 7. And then I have to graph those with the y values of each term. So my first order pair should have been 1, -22, then 2, -13, 3, -4, and so on. All right, let's take a look at this example. This is how to find a term if I'm missing one. So during their routine, a high school marching band marches in rows. There's 1 performer in the first row, 3 performers in the second row, 5 in the third row, and so on. This pattern continues. Use this information to figure out how many performers will be in the 20th row. Now, obviously, we could just keep drawing, but to draw 20 rows would be a little bit tiresome, so we're going to make use of what we know about arithmetic sequences. The difference between any 2 consecutive rows is 2, right? In this row I have 1, 3, 5, and so on. So my common difference is a +2. So we're going to actually use the fact that arithmetic sequences are linear to write an equation. So here my slope is 2, because remember that's my common difference. The common difference is the slope. One of my points that I can use is 3, 5. The third term is the number 5. And then we're going to solve it for x equals 20. So we're going to use point slope form. So the point I plugged in is 3, 5. Of course, you could plug in the point 2, 3 or the point 1, 1 if you wanted to. So plug in what you know. My slope is 2 because that's my common difference, and I simplify. And I get y equals 2x minus 1. So now I want to know what's happening in the 20th row, what's happening in the 20th term. How many people are in the 20th row? So I plug 20 in for x, simplify, and I get 39 performers who will be in the 20th row. And of course, you could keep going. You could just keep adding 2. 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 2 is 7, and so on until you reach the 20th row, and you would get 39. That's another way to do it. But we should get familiar with doing it with the formula as well. All right, we're going to skip that one and move on to geometric sequences. A geometric sequence is different than an arithmetic one. It's still a list of numbers, but this time the ratio between successive terms is a constant. So instead of subtracting, I'm dividing, okay? That constant ratio is called the common ratio, and we usually use the letter R to denote that. To find the common ratio, I take any term and I divide it by the term before it. So if we look at this sequence that I have down here, if I take any terms, if I take 16 and I divide it by the term before, 8, I get 2. 8 divided by 4 is 2, 4 divided by 2 is 2, and so on. So 2 is my common ratio. That means I'm multiplying by 2 to get my next term. So the next term here would be 32. Then I'd multiply by 2. My next term would be 64, and so on. The rate of change in an arithmetic sequence is constant. In a geometric sequence, it's not. My ratio, what I'm multiplying by, is the same, but the difference between the terms is not constant. So when we graph this one, it is not going to be a straight line. So be careful. If you're doing ratios like 16 divided by 8, make sure you always do the ratio the same way to check and see if it's equal at every step. All right, so is this sequence geometric? Well, we're going to find the ratios of consecutive terms. So I'm going to do 20 divided by 8, which is 5 halves. Then I check 50 divided by 20. It's also 5 halves. Then I check 125 divided by 50. That's also 5 halves. So this is a geometric sequence. All right, now if we check this one, if I do 30 divided by 19, I get about 1.58. 41 divided by 30 gives me something different, about 1.37. And 52 divided by 41 gives me something different again, 1.27. So this is not a geometric sequence. Okay, you guys try this one. All right, this is a geometric sequence because 8 divided by -4 is -2. -16 divided by 8 is -2. And 32 divided by -16 is -2. So notice that in a geometric sequence that has a negative common ratio, since I'm multiplying, it goes from negative to positive. So -4 times -2 is 8, times -2 is -16, times -2 is positive 32, and so on. All right, this one is not geometric. You should have found that your common ratios, when I do 9 divided by 2, I get 4.5, but the other ratios did not give you that same thing. All right, take a look at this geometric sequence. They're telling me it's a geometric sequence, and we're going to find the next 3 terms. So first I find the common ratio. To do that, I do 15 divided by 10, because that's probably the easiest one to do, which gives me 3 halves, or 1.5. So to find my next term, I'm going to keep multiplying by 3 halves. So I need to find the next 3 terms. So I'm going to do 22.5 times 3 halves, which gives me 33.75, times 3 halves again, and again to get my next terms in my sequence. So those are my next 3 terms, and now we're going to graph and see what they look like. So you have a place to graph this on your paper. Again, my domain is 1 through 6, 1, 2, 3, 4, 5, 6, because there are 6 terms, and each of those makes an ordered pair. So my first ordered pair is 1, 10, my second ordered pair is 2, 15, and so on. Notice this is not a straight line. It looks a lot more exponential. Okay, so geometric sequences graph exponentially because they have a common ratio instead of a common difference. So here's kind of a side-by-side comparison of arithmetic versus geometric sequences and how they graph. Arithmetic graph linear, geometric sequences graph exponentially. And notice the equation is r, which is my common ratio, to the x. So r to the x, that would be the equation we would use instead of using point-slope form, or a linear function, it's r to the x, an exponential function. All right, now we're going to practice classifying. We're going to figure out whether or not this sequence is arithmetic, geometric, or neither. In this case, it turns out to be arithmetic because there's a common difference. If you look at what they're doing with the ratio, there's not a common ratio. So you guys try this one. This one should be neither arithmetic nor geometric. One more.